Hello, everyone. Welcome to today's webinar entitled Precision Ag Applications with Calian GNSS Antennas. Be ready for 2025. My name is Khalid Abdallah, and I'm the Sales Success Manager at Calian. I'm so excited for today's webinar. We have an outstanding lineup of speakers, each bring a wealth of experience and expertise in the GNSS field. I'm joined today by Neil Hamilton from uBlocks, Ken McLeod, Joseph Botros, and Gord Ackland from Calian. While I have your attention, and before I kick things off, I'm going to cover a few housekeeping items. As we are going through the webinar today, feel free to use the question box in the webinar panel to ask your questions, and we'll address as many as possible at the end. This webinar is being recorded and will be added to our webinar library in our resources. We will email out the link to the recording within the next few days. Make sure to stay to the end. We have an important announcement to make. So the purpose of today's session is to provide you with valuable insights into GNSS precision agriculture applications, offering cutting-edge information to support your operations. We'll begin with a brief overview of Calian and uBlocks, followed by a discussion on the significance of the precision agriculture industry and its key applications. Next, we'll address the challenges faced in GNSS and explore effective solutions, including smart antenna technologies and correction methods. Finally, we'll wrap up with a Q&A session to answer any questions you may have. So Calian is a public company formed more than 40 years ago in Ottawa, Canada. We are on track to become a billion-dollar company in 2026. The company currently has 3,700 employees and operates across 5 continents. Calian has 4 divisions: Advanced Technologies, Health, Learning, and IT and Cyber Solutions. We engage with the agriculture industry through both our Calian Agriculture Group, who specialize in advanced agriculture solutions, and Calian GNSS. both Calian GNSS established in 2009. We are a leading manufacturer of GNSS antennas and accessories. Our antennas are Canadian made. We also offer engineering services such as antenna customizations and tuning. We are known for our quick fulfillment, high quality support, technical guidance, innovative technology, and competitive pricing and high-quality products. Calian GNSS is recognized for its innovative technologies and patents. Without further ado, let's start with Neil Hamilton.
Very good. Well, hello everybody. Nice to be with you all. I'm head of growth for the service product lines at uBlocks, and I'm delighted to be invited to join Calian and yourselves today to talk a little bit about the agricultural market. A quick look at who uBlocks is. We are a 25-year-old global leader in manufacturing, developing and manufacturing GNSS chips and modules. Many of you may have heard of those products if you've worked with particular types of technologies like this over the years. You may not know that we also operate and manage a network of satellite reference stations around the world, which enable us to deliver a world-class GNSS correction service that will be kind of weaved into the today's webinar to explain why that is a thing and how that works. But it's a combination of our hardware and these services that enable our partners such as Calian to deliver really amazing solutions for particular verticals such as precision agriculture. So we'll be coming on to some of that during this session. So why are we all here? Probably bringing us all here today is the subject of global population growth. You know, over the next few decades, we see different graphs, but we're on target in the next 10, 20 years to become a population of 9 billion. And with that comes a need to produce maybe 70% more food than we do today. And if you look at the blogs and the content on the internet, you know, we do see that despite technological developments like industrial bioreactors, which is growing protein at scale, agriculture is going to play the major role. But the challenge with this is who's actually going to grow the food, because as we also see, as demand goes up, we see that the trends show us that we're seeing a continued reduction in the global agricultural kind of staff or labor force effectively. We see that young people's aspirations these days are higher than they ever have been, and they're better educated, so they're attracted to better jobs with better work-life balances, and they don't want to work hard jobs in fields at night, early days, this kind of thing. And for those that do not want to work on the farm, that do want to work in farming, so family farmers, for example, it's getting really tight to actually draw salaries and run their lives, because we have more volatile crop pricing, which is partly related to maybe not just in international challenges, but the increasing unpredictability of weather is really affecting yields. So again, all of this is really impacting the profitability of agriculture, and so there's no surprise that we start to see that graphs or the demands for machinery, smart machinery in the ag world increasing. Our next graph shows us what we see in terms of these types of this type of growth, and again, different analysts have different kind of forecasts, but they're all radically increasing very quickly. So there's no surprise there, and we see that it's technology that's being used to overcome these challenges. But let's take a look at some of those applications that we can cover off today. So most agriculture applications are now becoming very digitized, and here's kind of some clusters of those types of examples with maybe an application note underneath them. And you all might be working on different areas within, or different sectors and segments within these types of applications. I mean, typically auto steering has been the most popular digital satellite-based application for the last 15, maybe 20 years, maybe more. In that situation, you've got a human sitting in a tractor cab, but some of the fields you find in the US and certainly in places like Brazil, they're huge. And so to ensure the accuracy of the pass-to-pass going up and down the fields with the tractors, they've got to be accurate within a few inches of where they're sowing seeds and things like this. So this is where we introduce this precise satellite feeds, if you will, to ensure that the receivers on board the tractors know exactly where they are precisely, and they can repeatably hit exactly the same spot time after time. And many tractors are sold, or vehicles in combine harvester and all these types of vehicles are often sold with some of this kit pre-embedded, but we often, well, there is very much a booming aftermarket as well for these types of applications or these types of products. And again, Calian has products to suit this kind of area of market as well. What's also coming are cab-less tractors. So again, we're involved with a number of companies who are producing a cheaper tractor that doesn't need a human operator, but because the precision market is becoming more affordable, satellite technology combined with other sensors is becoming so precise, we don't need the people anymore on board. And so farmers are actually building fleets of these tractors to conduct jobs quicker. And attached to these tractors are often implements. If we look at the jobs that need to be done, you've got the ploughing, you've got the planting of the seeds, the irrigation, the thinning, the spraying, the harvesting, and other tasks that are needed. And all of these are now adopting different elements of precision to achieve them, often to save on water and on pesticides and things like this, so we can reduce the costs, thus increasing that profitability for the farmer. For example, when you sow seeds these days, you can sort of come back to exactly the same spot within inches in that field. And even if the field's 3-4 kilometers square, which often is the case, there is kind of an inbuilt map of where these rows of seeds have been, planted. And with weeding applications, we see that AI is now being introduced as well. So effectively, you can not just come back to the same spot, but with AI and visual inspection, you can work out, and we see out many of these applications, you might be working with them, where the camera systems can now work out and instruct the sprayers or the thinners that often are referred to say this is a weed or this is a crop. And this is happening at speed, because typically these implements have been pulled by tractors at maybe 3, 4, 5 miles per hour. But if you can compute that quicker with technologies from companies like NVIDIA, you can travel quicker now, 10, 12, 15 miles per hour, and still do the same spot spraying or the same kind of specific job in the field. So now we can cover more ground much quicker with maybe fleets of robots and start playing catch up with the amount of food that needs to be produced, because we can process more, we can do more farming effectively, and 24/7, because there's no humans involved, so fatigue isn't a thing. So again, you can see the benefits where this all plays a role. Another kind of interesting, groundbreaking observation, certainly I've seen in the last few months, has been around fruit crops. So again, I'm not a farmer, but I'm always fascinated by the applications that we come across. And so often fruit, because of the hazardous environments such as frost and cold and rain, fruit bushes and trees are often grown in huge polytunnels. And polytunnels obviously have got a clear line of sight to the sky, which is great for precision because we need to see the satellites. But then you have this incredible kind of multitasking robots where in the evening time they can precisely travel in amongst the fruit bushes. They can be applying UV to all the plants to kill any fungi that might be growing. But at the same time, so two jobs being done at once, they can be visually scanning the crops and working out which crops will be ready this week or this next few days to be to be harvested, and that can be all sent straight to a farmer who can then start negotiating their pricing because they know how much they've got to sell. So it starts to improve the overall kind of productivity and the economy involved in farming and harvesting. So that's the amazing thing about robots. We see more of these robot applications that are doing more things than just one job. They're doing a number of jobs at once. So that's just a few examples there. And then if we look at maybe the common thing happening behind the scenes, the common thing happening is all the engineers involved in building these kind of examples on screen, as you see. The common thread is they're focusing on the job to be done. They're focusing on autonomous steering. They're focusing on spraying the right crops or predicting yields. It's the applications they're involved in. None of the engineers we generally find, certainly in many of the new young companies that are fast growing now and receiving investment and starting to kind of find new markets, none of the engineers are necessarily GNSS experts, and they shouldn't be, because it's not necessarily their field. They're focusing on actuators and robots and this kind of thing. And so my final slide is really just highlighting before we get into the subject matter, that they shouldn't have to worry about some really complex stuff, not just the satellite constellations and the bands you need to use, but we have solar events all the time that affect satellite signals. So you would be amazed at what happens before, as you see tractors going up and down in fields, the technological involvement of what's happening from the satellite perspective is incredible. And even there's a map here you can see on the ground, on the image here, some arrows pointing on the Earth's surface. Not only have we got problems in space, the ground we stand on is moving in different directions depending on where you are in the world. So if you want to come precisely back to those plants that you planted, all of this has to be taken into account. And that's not the roboticist or the software developer's job. That's our job, working with Calian. So maybe we can take a deep dive now. Hand over to Ken to talk us more about those challenges.
Thank you, Neil. Yeah, I'm Ken McLeod. I'm the product line manager here at Calian. I've got 30 years experience in the GNSS industry. Believe it or not, I started working with GPS when there were only 4 satellites in view, so I've been at it a while. During my talk, I'm going to focus on the high precision GNSS positioning techniques, the challenges required to achieve 10 centimeters. So some of the applications Neil mentioned don't really require high precision, but most do. So we're going to focus on those, and we're going to focus on accuracy and precision, typically 10 centimeters or less. In order to achieve these accuracies, you need a high quality GPS antenna and receiver. A cell phone system with a linear antenna can't achieve anywhere near the accuracy required. So it's special equipment that's required. And additionally, in addition to requiring high-end receiver and antenna, you need to apply corrections. So the corrections correct for a series of errors that that affect the GNSS signal. And not only that, but when you receive the corrections, they have to be received for a period of time so that the solution converges to the proper accuracy. And corrections are nowadays delivered by geostationary satellites, cellular, and UHF radio. Cellular signals are not always available, especially in rural areas. Geostationary satellites, signal can be blocked by buildings, trees, or terrain. And UHF radios have limited range. So just to emphasize the difference between accuracy and precision, if you look at the top left bullet, you can see that the point scatter is widely spread. The center of the bullet is truth. So in this case, you have low accuracy and low precision. And going to the right, you have low accuracy because you're not on the center of the bullseye, but you have high precision. And the bottom left, you have high accuracy and low precision. And of course, the goal is to have high accuracy and high precision so that you can return to the same spot as Neil mentioned and fertilize that the crop or weed apply pesticide to the weeds. Yeah, so the error sources, they're grouped into satellite error sources, atmospheric error sources, local environment, and instrumental errors. So on the satellite error side, the GPS orbits are predictions, so they're not accurate, or not as accurate as they need to be to achieve 10 centimeters. The satellite clocks are also predicted. The clock drifts with time, and there are biases. So the atmospheric errors are the ionosphere, which Neil showed in his slide, and the troposphere. Local environment is on the machine, for example. You can have multipath caused by the machine itself, and you can have signal obstruction caused by trees. Instrumental errors are antenna errors and receiver errors. So to give you a feel for the magnitude of these errors, over the table on the right, satellite clock errors roughly 2 meters. The satellite orbit errors are 2.5 meters. Ionospheric delays can be 5 meters, and at this time the ionosphere is very active. So in certain cases, if there's an ionospheric storm, you can have errors larger than 5 meters. The tropospheric delay is 0.5 meter, and receiver noise 0.3 of a meter, and multipath plus or minus a meter. Antenna design plays a critical role in achieving precision. The GPS signal is broadcast as a right-hand circular polarized signal. Think of it as a spiral emanating from the satellite to the antenna. Whenever the signal, so that's a direct signal. If the signal is reflected, it switches from being right-hand circular polarized to being left-hand circular polarized. So that's, and then when the signal is received, it has to be received at a point. So on the graph on the right, you see L1 electric phase center, and you see L2 electric phase center. And then below that, you see the antenna reference point, which is the coordinate that is derived from the GNSS observations. So think of an antenna as being the end of a tape measure. So any movement on the phase centers will affect the position. So we also, a high-end antenna also has to have a high-quality low noise amplifier that filters out of band signals and amplifies and provides a clean, pure signal in band. Joe will have more to say about precision antennas in his section. Another major source of error is multipath. So as I mentioned before, signals can be blocked, and in this case, this is an urban environment. So if you look at the red signals, they're being reflected and they're not being received directly. So that's probably one of the most challenging situations for detecting or minimizing multipath from the receiver's point of view. The antenna can maybe do something there. Typically in agriculture, the reflections come from the machine. If the antenna is mounted in a poor location, the surface currents can affect the phase center, and it could be multipath from the machine itself. So let's say if the antenna is poorly located and there's a reflection off a metal part towards the antenna, you have multipath. So both antennas and receivers have multipath mitigation techniques. Joe will mention the mitigation techniques that an antenna has. So as I mentioned at the beginning, there are in order to achieve 10 centimeter accuracy, you need to have corrections. And in this graph, you can see that there's precise point positioning, PPP, and you have PPP RTK and RTK. And then you can see the PPP RTK borrows a little bit from PPP and RTK. So starting with PPP, precise point positioning, the corrections that are broadcast typically over a satellite are the orbit correction, the clock correction, and the bias corrections. And that correction service is typically called state space representation, SSR, as you might see that in the literature. The RTK method, it uses a completely different technique. So it uses observations from a nearby base station that cancels out all of the errors. So if your base and rover are close by, the orbit error cancels, the clock error cancels, and the biases cancel. So that's the technique. PPP-RTK has borrowed a little bit from, a lot from PPP and a little bit from RTK, where you have you broadcast ionospheric and tropospheric corrections. Yeah, so the typical accuracy of PPP is 10 centimeters, and one of the drawbacks is with plain PPP is it takes about 10 minutes for the solution to converge. These things are always improving, but that's a typical convergence period. The PPP-RTK, on the other hand, has much faster convergence. It converges from 20 to 40 seconds, typically to 3 to 6 centimeters. And RTK, which is the fastest to converge, it's almost instant convergence, and it has an accuracy of 1 to 2 centimeters, depending on the quality of the instrumentation. So just to give you a feel for how the corrections are derived and delivered, the PPP and PPP-RTK don't really require a nearby base station, whereas RTK does. So there's a lot more hardware required for an RTK network. So station spacing with PPP is roughly 500 kilometers or more. PPP RTK is 300 kilometer station spacing. So with station spacing like that, you can provide an ionospheric grid and a tropo grid so that the solution converges more quickly. With PPP, those are estimated, and it takes a longer period of time. That's why the convergence is longer. With RTK, you typically have a very short baseline, so you need a lot of stations, and the separation between the base station and the rover is 20 to 30 kilometers. And corrections are delivered, PPP and PPP-RTK, the corrections are delivered over the internet or L-band. And of course, for RTK, it's internet or a UHF radio. So the corrections that are broadcast from a GEO are geostationary satellites are out on the equator. So you can see from the plot that the distance from the equator, the extension of the equator, not on the equator, they're 35, almost 36,000 kilometers away from the Earth. So that's a long distance, and compared to GPS, which is roughly, or GNSS, which is roughly 20,000 kilometers. So the signal has to travel further, and it's when it's received, it's quite weak. So as you, let's say in Canada or Northern Canada or Northern Europe, the look angle to the satellite is also quite low. So at here in Ottawa, at 45 degrees, the look angle is 33 degrees, so it's quite low on the horizon, and the signal is going to travel a long way. At 70 degrees north or south, the signal is seen at the horizon, so you can imagine that it's going to be very challenging to receive a correction at that latitude. But Calian, we do have antennas that have great low elevation angle gain, and this helps mitigate the problem, and Joe will talk more about that in his section. So just a quick summary. I'm going to look at the accuracy challenge, the mitigation, and the remarks. So GNSS signal blockage, which would be from trees or buildings. If you have a multi-constellation GNSS signal, you're likely going to see 30 satellites, and if you have blockage from 2 or 3, you'll still be able to produce a clean and robust signal. Multipath is divided into 2 categories. You have the near field multipath, and that's multipath that occurs on the machine, and then antenna placement on the machine is critical. And we have a lot of experience doing that, so we can advise customers how to mitigate that problem. Far field multipath, antenna design and GNSS receiver algorithms. We have antennas that have great axial ratio, and you know, with that technology, it supports the right-hand circular and minimizes left-hand circular signals. Antenna phase center precision, that's a good antenna design and calibration. All of our ag quality antennas are calibrated either by National Geodetic Survey in the United States or by GeoPlus+, who's the world leader in calibration. And you need this kind of accuracy to derive RTK, PPP, and PPP RTK quality positioning. As I mentioned, broadcasts from a geo are weak and they're broadcast over a long distance. So you need an antenna that has strong low elevation angle gain. And as I said before, we have one of those, and Joe will expand on that. All of our antennas have what we call extended filtering. So with the more and more cellular signals being broadcast, there's signals that can create harmonics in the antenna. And we have wide band filters from roughly 600 megahertz to 2000 megahertz, and they have 60 to 80 dB of mitigation. So over to Joe.
Thanks, Ken. Hello, everyone. This is Joseph Botros, Field Applications Engineer at Calian GNSS. So let's dive into technicalities. First, we have to consider why choosing the right GNSS antenna matters. Consider that the signals arriving on the ground are incredibly weak because the GNSS satellites are incredibly far away. The GNSS antenna is the very first component of the positioning system to process these signals. So if the antenna receives multipath, produces noise, shifts the phase of the signal, then the receiver cannot correct the resulting degradation to these signals. As the GNSS antenna is the first line of defense, its choice and its installation is critical and should be done wisely. Ken mentioned various challenges for obtaining good precision data for precision ag functions and other functions, of course. Here, antenna solutions are presented for several of these challenges. Going from left to right, for higher precision, you need low face center variation. For maximum accuracy, you need calibration. To compensate for ionospheric delays, you need multiband reception. Other sources of errors are compensated by corrections. To well receive those corrections over L-band, you need high low elevation gain, and multipath is mitigated by low axial ratio over elevation. So let's go through each of these one by one. Starting with tighter phase center. As Ken mentioned, precision is achieved by having an antenna with low phase center variation. The phase center is the point where the waves arrive. So at a given frequency or band, the phase center will vary with respect to elevation and azimuth. A good analogy is an incandescent light bulb. So that's for those of us, of course, who are old enough to remember them. Consider that the antenna reference point is the bottom of the bulb. The phase center then would be the offset location relative to the reference point, basically where the point where the light is emitted from. Phase center variation, or PCV, is the apparent variation of the PCO when you look around the bulb, and this is called by the varying thickness of the glass. In antennas, to minimize PCV, we employ the three following steps. First, more RF feed points, so generally 2 or 4. Second, a structure that is as symmetric as possible. And third, consistent and controlled manufacturability. The key takeaway point, a precise antenna has a tight PCV. As Ken mentioned, to maximize accuracy, you need a calibrated antenna. Knowing precisely the PCO location will give you the maximum accuracy. And this is provided by a calibration file, as Ken mentioned, NGS, GU++, which is in the NTEX format. So remember, an accurate antenna is calibrated. Moving on to ionospheric delay. As the signal travels through the ionosphere, which is a thick layer in the upper atmosphere of the planet, the signal incurs a delay which can add an error in your position measurement. That is because it adds an error in the measurement of the distance between the satellite and the antenna. By receiving at least 2 GNSS signals at different frequencies, like L1 and L2 in GPS, the delay can be calculated and removed to reduce the error. In addition, more bands and constellations increases access to more signals and satellites, which increases overall reliability of the GNSS system. Therefore, for higher precision and reliability, use a multi-constellation and multi-band antenna. Ken mentioned different types of corrections and how to access them. Corrections are the solution to the rest of the errors that were discussed, many of them. L-band corrections, which are received from GEO satellites, can be used to achieve centimeter level precision, squeezing the most out of the antenna and the receiver. Corrections provide the very best precision, so use an efficient antenna with high gain, especially at low elevation angles, to maximize L-band link margin, effectively maximizing L-band reception. Before moving on to the next topic, it is important to provide you with a tool for comparing the absolute performance between GNSS antennas, and that is the ability to read a radiation pattern graph. Take this one for example. You can see on the left, the magnitude, the left axis, that is the magnitude of gain in decibels. So you can interpret this as the sensitivity of the antenna to a signal. The higher the number, the higher the power level of the received signal. The bottom axis is the elevation angle in degrees. So at the center, that is zenith, or the point directly atop the antenna. At around plus or minus 90 degrees, that is horizon, which is directly to the side of the antenna. At the edges of the graph, that is nadir, which is the point directly beneath the antenna. The black curves are the right-hand circularly polarized measures, or RHCP, and the red lines are the left-hand, or LHCP. There are 60 phi cuts, or cuts in the azimuth direction, as in you are taking measurements over 60 different cross-sections of the antenna to look at the symmetry, the circular symmetry of the antenna. When there is less variation in these cross-section lines, as in it looks thinner overall, this means the antenna is more symmetric, which means a tighter phase center. Finally, when looking from zenith to horizon, the difference between the right and left-hand measures is representative of the axial ratio. So the bigger that difference, the lower the axial ratio, which is desirable, and we'll see why shortly. Now take a look at the radiation pattern of the Veristar antenna versus the Veriphase antenna. You can see that at low elevations, so if you look at the graph near around 100 plus or minus 100 degrees, the Veristar has significantly more gain than the Veriphase. And by significantly, you could measure probably around 3 or 4 dBs more. This is actually purposely designed, and it is accomplished by the element's unique integration of the curved petals. So why does this matter for precision agriculture? Well, high gain at low elevation, as we mentioned several times before, improves performance in difficult environments, maximizes reception of L-band signals from geosatellites. So it's especially important if you rely on L-band corrections and you're also at low, like really low or really high latitudes, plus or minus 70 degrees, as Ken was mentioning. The same design that provides this low elevation gain also results in low axial ratio over the entire sky view of the antenna, from zenith to horizon. The Veristar's axial ratio, as seen in the plot to the left, is almost always 3 dBs at horizon and less than 0.5 dBs at zenith as you go from the from GPS L5 all the way to the top frequency GLONASS G1. So the closer to 0 dBs, the better. As multipath reflections arrive at the antenna as left-handed signals, because they're reflected, a low axial ratio ensures that reception of those signals, those reflections, are as low as possible, causing minimal disruption to the wanted right-handed GNSS signals. Key takeaway: low axial ratio mitigates multipath interference. While not the only solution, the Veristar technology is a star for precision agriculture, covering all of these points very well. A tight PCV, the availability of calibration files, full band to GNSS coverage, high low elevation gain, therefore excellent L-band reception, low axial ratio over the sky view, therefore excellent multipath mitigation. And that's all available in embedded and housed models as shown. And in the next slide, we'll talk about other technologies. So other technologies such as patches, choke rings, and helicals, all of them have their purpose in the various precision ag functions. For example, drones can leverage the low weight of the helical antenna. Tractors can not only make use of Veristar, but the Accutenna patches as well. Crop dusters can use our aviation-grade ARINC patch antenna. Base stations with the Verichoke or the Veriphase. Robots and rovers can really use any of these technologies, patches, Veristar, vehicles, which depends on the specific requirements. So not only do we have standard antennas, but Gord will also be speaking about our smart antennas, which is our antenna technology integrated with the receiver. So to help with selecting the right antenna for your needs, the team is always available to offer clear guidance and paths forward. Of course, as we mentioned in the start, choosing the antenna is only really one part of the equation. the other, that's only one half of the battle. So I'll just give a couple examples. Take a look at these examples. To the left, you see a patch antenna that's integrated without a ground plane. In the middle, the metallic grill, as shown, is a risk for near field multipath interference. And to the right, the antenna, which you really can't see because it's right on the surface of the roof, proves to be an inadequate integration. So with guidance and care, the right antenna with the right integration will provide the very best performance for precision ag applications. Hence, the other half of the battle is properly installing or integrating the antenna into the vehicle or system. Of course, part of that means interfacing it with the GNSS receiver. Of course, there is another solution. There is another level of solution. That's where the antenna is integrated with the receiver inside in one package, such that we take care of that for you. And with that, I'll hand it over to Gord to explore how that is done.
Good morning, or good afternoon, depending on where you are. I'm Gord Eklund, responsible for business development on smart GNSS antennas and complementary PNT at Calian. Neil's introduced us to the what, how, and why of precision agriculture and the importance of centimeter level GNSS. Ken introduced us to some of the inner workings of GNSS and how centimeter level positioning is attained, while simultaneously detailing the challenges in achieving it. Joe showed us how Calian GNSS antennas mitigate these challenges. I'm now going to talk about the remaining exposure in precision agriculture, the remaining wild card in implementation of your application's GNSS system. Between the antenna and the receiver, there remains a fundamental issue that might affect system performance. The traditional partitioning between the antenna and the receiver versus the rest of the system. The almost universal model is that today, the antenna is connected directly to the system by a coaxial cable terminated by an SMA or a micro miniature coaxial connector. This was probably fine in the age of 2.5 meters or worse circular error probability that you get from a phone. You didn't expect any more precision than that. In the centimeter level precision age, not paying attention to the quality of the signal between antenna and receiver can quickly induce noise from multiple sources into the signal. Sources of interference such as Wi-Fi, Bluetooth transmitters, USB cables, high-speed buses, even display elements, all of these and more lead to unanticipated issues. On top of this, a longer cable requires more antenna gain, which can further amplify induced noise that can impair your receiver. Leaving this exposure for system developers to manage is not an optimal situation for rapid market expansion. Calian's solution: change the GNSS system partitioning. Move the receiver onto the antenna side of the cable and use digital signaling to present already decoded GNSS information to the system. This method allows RF experts to manage the exposure window by proper shielding, minimizing the LNA path, physical isolation from noise sources, as well as other techniques. It also allows longer cabling, as now the signal is digital and can be regenerated with 100% accuracy, because that's what digital transceivers do. Calian's blueprint for a robust GNSS appliance, or smart antenna, is to start with one of our antenna platforms: patch, helical, cross dipole, choke ring. It depends on the application. Pick the right receiver for the job. There are a wide variety of receivers with different features. Dual band versus triple band fractions such as PPP-RTK, RDK, SBAS, Galileo Haas, centimeter level augmentation service over L-band. And by the way, this is a point of integration that seems to be a tripping point for a lot of developers, adding L-band, inertial measurement units, moving base precise heading, and much more. We have variants of our smart GNSS antennas that cover the waterfront. Integrate properly, usually the domain of RF experts, which you may or may not have on your team, but we have on ours. Add an appropriate digital interface. RS-232 is typical. RS-422 for longer distance, USB for convenience, CMOS for many drone applications, Power over Ethernet for non-mobile server environments, and in the future, CAN bus, automotive Ethernet, Wi-Fi, and Bluetooth. An often overlooked benefit of this new partitioning is that improvements in antenna and receiver technology are localized in the GNSS appliance. On the system side, only software needs to be upgraded when, for example, moving from dual band to triple band GNSS receivers. The details are abstracted from the system by the serial interface. Early precision ag participants have been companies with deeper pockets, demonstrably a handful of major GNSS capable companies that were already GNSS proficient. We all know who they are. We are now approaching, if not in it, the tornado phase of the market, where participants are proliferating and are usually smaller, nimble companies. As Neil emphasized, this rapid expansion is characterized by application specialists using platforms to innovate quickly, relying on open frameworks to deliver, for instance, robotic or drone functionality, while they focus on their application. For example, analysis of material application on crops, or steering down a row of fruit lattices. The GNSS appliance is no different. It is equally a resource that companies don't want to differentiate themselves on, but need to work out of the box to get to the market quickly. It's not just the RF aspects, but the complexity of using highly integrated receivers is also something that needs to be abstracted, just as nobody needs to program a printer to print a Word document. Most development teams don't have or want to acquire the expertise to understand the full API for a modern GNSS receiver, even the simplest ones. They are designed for a broad spectrum of use cases, and subject matter expertise on a receiver is not a differentiator for end product development. This is especially true right at the crucial beginning of a project. Tools for using, evaluating, and monitoring GNSS that can assist in field testing need to be acquired without delay. In the same vein that companies creating smart GNSS antennas solve the RF problems by moving the receiver to the antenna side of a digital interface, these companies deeply understand interface and programming of the GNSS receiver and can provide tools to help developers work with the receiver environment without creating conflicting scenarios by enforcing rules for interacting with a device and creating a powerful evaluation environment. For instance, setting up the receiver as a base or a rover, homing to, authenticating with, and using a commercial corrections provider, tuning an IMU dynamic model based on the intended application, toggling constellations on or off, evaluating performance, and performing logging for long-term analysis. Following the trajectory beyond evaluation kits, a robotic or drone framework has an OS, and there are open source choices such as ROS2 or RGPilot. Precision Ag is a natural for these platforms. In a nutshell, developers want to work on their differentiation, not reinvent the GNSS wheel for equivalence. To that end, the Smart GNSS Antenna/Appliance with accompanying drivers for the major robotic and drone platforms is a huge accelerator for precision agriculture. But don't stop there. The Smart GNSS Antenna is capable of supporting multiple types of corrections from local RTK to commercial services to PPP RTK and other state space representation solutions. Unique SKUs can be created that pair a Smart GNSS Antenna/Appliance with any of the compatible commercial services available right out of the box. At Calian, we currently support u-blox's Point Perfect, Point 1 Nav Polarity, and Swift Nav Skylark out of the box. Finally, with Precision Ag expanding beyond being the domain of the GNSS old guard, who typically market precision with their own locked-in rover and base solutions, and even their own corrections, new entrants may choose to deploy local RTK and need a base solution. This is also an area where a Smart GNSS antenna can be utilized, right up to continually operating reference station grade for more long-term placement, such as on an extensively sized farm. The VCS 6000XF Smart Choke is one of the first basic CORS offerings that puts all of these integration techniques into play to enable new entrants to affordably design their own solutions and even develop a solid base solution of considerable reliability. To summarize, as you can see, a smart GNSS antenna/appliance approach empowers new entrant companies to navigate the GNSS aspect of their systems effectively, reducing the complex system requirement to a plug-and-play module.
Thank you, Gord. And thank you, Neil, Ken, and Joe, for the powerful information shared today. Before we move on to the question and answer period, in the introduction of the webinar, I had said, wait till the end for an announcement that we're going to make. So to help you be ready for 2025, we are offering 30-minute consultation sessions for your precision agriculture applications. There's no cost to this, and I'll be reaching out to you via email for more information if you would like to book a session with us to go over your applications and how we can support you within the GNSS applications for precision agriculture. So as we move on to the question and answer period, the first question we got is how often does one need to calibrate the antenna?
Yeah, I think I can answer that one, Khalid. So whenever an antenna is calibrated by either National Geodetic Survey or by Geo++, they calibrate more than one antenna. So you have within the family, you will have 5 of that type calibrated, and then what the calibration unit does is they do a weighted mean and determine the phase center offset and the phase center variation. So then all antennas that are bought in that family are believed to have the same calibration. So you don't have to calibrate the antenna over time. The physical nature of the antenna doesn't change, and that's what that's where the phase center is located. It's a physical location as well as electrical, but it's derived by the physical nature. So it's only maybe the highest precision, for example, maybe the International GNSS service, the reference frame stations would be calibrated from time to time, but it's not common to calibrate over time.
Thank you, Ken. The second question we have is, we are developing a wheel-based field robot. It will operate in orchids. What antenna will be best suited? The questioner continues to say that they've read that new L5 signals are improving the tree shadow interference.
I can grab a hold of that if you like, Khalid.
Thanks, Gord.
So if we're talking about a smart antenna, then I would recommend our TW5790, which has a built-in inertial measurement unit and has L-band reception. Today, that product is L1, L5, but we can also very quickly deploy it as, L1, L2, but we can very quickly deploy it as an L1, L5 unit. So it's a USB connection, if you like, or an RS-232 connection. It's a surface mount, magnetic mount. And if you want moving base precise heading, there is a variant called the TW5794. So that has a U-Blocks, the 5794 has a U-Blocks ZF9P receiver on it, and the TW5790 has a ZF9R U-Blocks receiver on it.
Thanks, Gord. The third question is, how do I start with what solution is best for my application?
I guess that depends on whether it's you need something light, if you need something stationary and very accurate over time, and it's going to stay there for quite a while. For instance, a drone application, you want a helical antenna or even a cross dipole SSL 990 or something like that, very light with great gain over the various elevations. Ken?
Yeah, I was thinking along the same lines. It also depends on, for example, in the correction services, if PPP is good, if you can wait 10 minutes for the solution to converge. And if you can't wait that long, and you can have the PPP RTK, and then of course if you want instant convergence, RTK is the solution. So if your application is such that you're in a wide open field, corrections are going to be delivered reliably, so you don't have to worry about it. So it's all depends on your environment and your application, I think.
Thanks, Ken. Yeah, so it depends on the application. So first we need to go into your application, and this is something that we can do over our consultation session if it's something you're interested in. This is the last question that we've got, and then we'll wrap up the webinar. For corrections, Swift, point one navigation, and point perfect, are they interoperable? For example, areas where Swift is not available, can point nav corrections be used?
Yeah, I can take that one. So yeah, theoretically, all the services, it depends on your receiver and your setup, I would say, but I guess the application should be using NTRIP, using an IP connection to deliver, or receive RTCM corrections to your receiver. So I believe all the services offer something similar there. So that is, you could provide interoperability. Of course, I'm going to recommend that you just use Point Perfect because its coverage is ubiquitous. So you shouldn't find there's any patches anywhere that's missing. But yeah, it's the same technologies underneath, so the receivers are pretty open. So I'd say yeah, interoperability is possible.
Perfect. Thank you, Neil. Actually, we have a couple more minutes. We just got one more question, if that's okay. The question is, okay, your signal base cores network-based receiver, what are the communication languages? CMR, CMR plus, RTCM?
On the smart choke, we use a Septendrio Mosaic X5 receiver, and it's capable of receiving all of those protocols or transmitting them.
Okay, and a follow-up question to that. Additionally, does the smart base have integrated cellular connectivity?
No, that would have to be added on the other side of on the system side. We don't have integrated LTE on that.
Great, thank you, Gord. Okay, that concludes our question and answer period. I want to thank the speakers today, Gord, Ken, Neil, and Joe. This has been a lot of fun and very informative session. To all the attendees, thank you so much for your time. We really hope this was informative for you as well. And we're here to support you. We will be sharing a recording of the presentation as well as the slides. In the last slide, there will be contact information for us. So if you have any follow-up questions, whether about precision agriculture and its applications or more technical questions, please feel free to reach out. Thank you so much for your time, and have a great Thursday.